Hey everybody, welcome to another CS302 assignment video. This one's going to be Mario Kart. And of course, there's our picture of the blue turtle shell, which is definitely something you don't want to see whenever you are in first place in the race. So we're going to basically use a priority queue to maintain several set of cars, their relative ranks in the race, which cars in first place, second place, and so forth. So we're going to use a priority queue to maintain all that. So obviously, with a priority queue, we have like an array or vector, and then it emulates a binary tree. And of course, the root of this tree will contain the car that's in first place, etc. So basically, in this particular simulation, there'll be no items you can use. It'll be just simply only a race. I mean, obviously, if you were to use items, the obvious best solution or best technique would be to be always in second place all the time and always have that red shell primed and ready at all times. So whenever the first place person is close to finishing, you launch that red turtle shell, take them out, and of course you take the first place. And of course, I don't know how that's going to maintain your friendship after that, but that's obviously a very optimal way to play Mario Kart. But right now we're going to just simply stick to just a racing simulation. So let's go ahead and go over all of our data types you're going to have to implement in this sort of simulation program. Okay, so basically we have to maintain a set of racers, and each racer in the simulation will have a RacerType struct used to maintain that racer. So each racer will have a name. So set of, we obviously will have Mario, Wario, Luigi, and so forth. Several different racers. So each one will have a name, and you have to store their distance remaining. So how much distance left they have until they finish the race, and their current speed. So this simulation is going to simulate 1 second of the race. So each second will have the racers update their speed, which will be in feet per second, I guess. And the distance will always be in feet. So it'll be a really short race, but good enough for this simple simulation. Now you're wondering, what is that operator question mark doing over there in this struct? So first of all, there is no such thing as a question mark operator. So if you try to actually compile this and you think, well, why can't this question mark operator work? Well, it's written here in red. I have here in red that there is no such thing as a question mark operator. That's there for you as a choice to overload an operator. So remember, for a priority queue, we have to constantly compare, the parent with the children, or we have to compare the two siblings to each other to see which element would be further up in our tree, right? So we want to sort of make a generic priority queue class, and we can have to use this operator. Either we can overload less than operator, less than equal, greater than equal. So you can overload more than one operator if you want for this struct. But you're going to have to use the operator in your class priority queue, which I'll go over a little later in this video. So the whole purpose is so that way we don't actually sort of access the distance remaining field within the class priority queue, so that way we make our class generic. But anyway, we'll get to that in a little bit. So the idea is that we want to overload this operator in such a way which will help us design our priority queue. So basically, the parent element will always be in the lead. So this operator will have to overload the following sort of logic to maintain elements in our priority queue. So whenever we compare, let's say, the parent with the children, or parent with both children, or with a single child, basically the parent will always have to be an element that's further along in the race. So basically, if we're comparing the parent and the child, if the car that's further in the race, or less distance remaining, that element would be at the parent level. So we have to, compare the parent and the child, and if we have to verify which element is further in the race. So obviously this less than operator or greater than operator, whatever, overloads this logic. So the car that has less distance remaining would be in the lead. Now, let's say if you're comparing these two cars and they have the same distance, then you're going to have to basically compare which car is traveling faster currently. So if the two cars are the same distance away, but then if that's the case, we check which car is going faster, that car would be ahead in the race. Now, if let's say between two cars, if let's say their distance traveled is the same and their speed is the same, then we're going to just simply use their name and whichever name comes alphabetically first is going to be ahead. And of course, the parent will always be ahead of both of its children in the race. Obviously, the root of this tree would be the one that's in first place. So as we insert, remember, into a priority queue, we have to constantly compare the parent with the child, and whichever one is smaller or larger, according to whatever operator you overload, you have to make sure you bubble up the correct element up the tree to make sure that the parent is always further in the race than the child. So anyway, I think I might have overdone that explanation, but that's what you have to actually do. So now let's go ahead and discuss the actual contents of our priority queue class. So here's our priority queue class. So notice it's going to be a template class. That type basically is going to be RacerType. So in main, you would declare a priority queue and use RacerType here. So all these types will be RacerTypes. That's why we want to overload the operator to make sure we can sort of correctly do all this. So anyway, let's first go into our vector heap array. So this heap array is going to be just an array of type, or essentially it'll be an array of RacerType. So this is going to just maintain all the elements in our priority queue. This heap array will be our array that emulates this binary tree representing a min or max heap. So it's up to you which one you want to use, but as long as we implement this structure that the parent is further in the race than both its children. So there's your heap array. So then we'll have our constructor priority queue at the very top, and this constructor just simply sets up our empty priority queue. Now, once again, in class, as you might have remembered, I always use index 1 as the root element, or the root element, or in this case, the leader of all the racers. So index 0 of heap array was really sort of a dummy or garbage value. So if you do want to use this structure or this approach where index 1 is your root, then in this priority queue constructor, you're going to have to essentially push back some dummy value or just do a resize. So heap array.resize 1. So that way, that index 0 element will be just some placeholder value, whatever you want to call it. And as we insert elements into our structure, the first element will go into index 1 of our array, which index 1 is going to be your first element. Now, of course, if you rather have it where index 0 would be your root element instead, that's fine. If you want to do that, then of course the priority queue constructor would have nothing in there, it'd be empty, because essentially your heap array is empty already, so that's all you have to do. And of course, if you do that, you have to make sure as you compute the left and right child indices and so forth, you may have to sort of do an add by 1, do some kind of offset to make sure it sort of works out. That's why having the index 1 being your root is sort of makes it much easier to visualize the math and so forth, but it's up to you entirely. So that's going to be your constructor. So now the pushback function. So pushback is going to be equivalent to that insert function I might have used in class. So pushback seems to be like the more generic approach for how to insert to the back of your priority queue. So obviously in pushback function, you have this parameter you're being passed in. You're going to call the heap array's pushback function and pass this parameter into that function. And then you're going to call bubble up. And you're going to pass the index of the most recently inserted element to the back of your heap array you just inserted. You're going to pass that index of that recently inserted element into bubble up, which is going to do all that reshuffling of elements in your heap array to maintain this min or max heap. So that's all you have to do for pushback. Now for pop front, that's going to be equivalent to what I went over in class with delete or whatnot. So pop front is going to return that root element, and then of course we'll perform that priority queue deletion. So of course, just you have to make sure that you want to maybe store the current root into a temporary variable, and then perform those same steps I did in class for how to do a deletion from a priority queue. Remember how that works? You overwrite the root with an element, then you bubble down from index 1, and of course return the previous roots. You have to store the root element into a temporary variable, then remove that root from your priority queue, calling bubble down and doing a little bit of work around there, and then of course return that root. So that's all you have to do. So I kind of went over this in class, and I want to really overdo it here, but that's that. Then in get front, obviously return heap array index 1 or index 0, depending on which element you're going to designate as your root element of your priority queue. Is empty. Returns basically true if there's nothing in your priority queue, and false otherwise. So of course, once again, make sure you're aware that if you do have where index 1 is going to be your root, then if you have only one element in your priority queue, that means it's essentially empty because index 0 doesn't count as an actual value. But if you don't do that, then of course, if let's say you choose index 0 to be your root, then obviously index 0 is going to be, if you have 0 elements in your priority queue, that means it's obviously empty. So that's basically how you would do that. So just to sort of, I guess I might have went a little too fast here, but for the pop front function, after you take the last element, overwrite the root with it, you want to do a pop back on heap array to remove that last element and then bubble down from the next one. So just in case if I skip that. And of course, bubble up and bubble down, the same as in class. You pass index into this function, and then of course bubbling up, you do that same logic, the same explanation as in my class video / whatever I covered in class. So that's all you gotta do over here. Of course, these two functions can be either recursive or using a loop, but same logic as I sort of demonstrated many times in class when I went over priority queues. So that's basically it. And of course, just to make sure I don't skip this, so since you're going to be using, the type is going to be, how shall we call it? It's going to be that RacerType. So whenever you're doing bubble up and bubble down, remember, you have to compare and make sure, let's say if you have a min heap, for example, then the parent must be less than the child. So here's where you're going to be using that operator that you overloaded for that RacerType. So instead of, saying, let's say, for example, heap array at index 1 dot distance traveled is less than heap array index 2 dot distance traveled, that's not a good implementation of priority queue because this is a templated class. You can't assume the type of this of the heap array. So you have to use that objects less than or greater than operator to be able to compare elements when you're doing your bubble ups and bubble downs. So just want to make sure I sort of cover that before I go on to the next section. So now we're going to go over the input, output, and of course the actual main algorithm for this program. So for this program, you're going to basically read in two input files. You're going to open up two file streams. The first file stream you're going to read is going to be just from this file stream. You're going to have your racers file. So the first file stream will contain a list of all your racers. So all of these are going to contain the names of the racers. So what you're going to have to do is you have to push sort of a struct object into your priority queue. So in main, you create a priority queue of type RacerType. So you'd have to read the name Mario. You're going to insert Mario into, so you would maybe create sort of a local or temporary RacerType object in main. Assign Mario to its name field, 50 for its distance traveled, and then 0 for its speed. And then you're going to take that and push it into your priority queue. Then for your next name, Luigi, you assign Luigi into some temporary RacerType struct object, and then assign 50 for distance traveled, 0 for its speed, and then push that into the priority queue. And then just next name one by one, just keep doing that. So you're going to have all the elements currently pushed into the priority queue, which means those are going to be the elements that are going to be currently in the race. So the second file you're going to have is going to be the simulation file, which is going to basically allow us to randomly assign some value to each racer. So I didn't want to use a rand function for this because if you use code grade with rand, it's going to cause all kinds of problems. This is going to be reading a value from this file is going to be our quote unquote random number to reassign for the speed of each racer. So that way we'll have the same random numbers we're going to be using. So that way the simulation should be the same for all of us, whether you're on a Mac or Windows or Linux or code grade, it should be all the same. That's the purpose of this file basically. So let's go ahead and now talk about what we're going to have to do in main to actually simulate this race. All right, so now that you have everything in your priority queue, now you can actually simulate this race. So what you will do, this is all going to be, so this content, I guess 1 through 5 is all going to be wrapped around in one big sort of loop. The loop is going to be that if every car has finished the race, then it's going to stop. So this steps 1 through 5 would be really inside of one big loop, basically. So what's going to happen is the first thing you do is you're going to pop an element off the priority queue. The first thing you'll do. Then you check. If that distance remaining is 0 or less, then that racer has completed the race. So you're going to have to basically output that racer's name along with their rank. And that's all you're going to do in this case. Now, if let's say this racer has not completed the race, let's say we pop Mario off of the priority queue, and it has not completed the race, so the distance remaining is not less than 0, then you're going to go ahead and read from this file. You're going to read this number 0.88. You're going to assign that value for Mario's speed, and then compute its distance remaining. So we're going to do 1 second of the race. These are all going to be feet per second. So you just update this speed to 0.88, and then you subtract that speed from the distance. And then you're going to go ahead and sort of push it onto a vector temporarily, just to sort of maintain elements that are still in the race. You're going to put them back into the priority queue in a bit, but what you'll do is you remove it from the priority queue. If it didn't finish the race, update the speed, update the distance, and then put it into a temporary vector for right now. And you're going to keep doing this until there's still something left in the priority queue. So you're going to update each racer's speed and their distance traveled. And each one you pop it off, update their speed and distance, and put it into a vector. That's all you're going to do. Now, if one of them has finished the race, then you're going to just output it and then not put it into a vector. You're going to discard that element because that element is no longer in the race. So you have that part taken care of. So then what you do is you're going to then push all of them back into the priority queue and then rerun a simulation. So every sort of step, every single second, you go into 1 by 1, pop element off the priority queue, and then read this number, then the next number 1 by 1, and assign these to each element that's popped off the queue. So you pop Mario first, that'll be its new speed. Let's say next element you pop off is Luigi, then Luigi will have 0.89. Next race you pop off this speed, and so forth. Then you go ahead and update their speed and distances, put them onto a separate vector. Once the priority queue is empty, you push everything back into the priority queue, which will recompute who is in first place. And then again, you just keep popping elements off, and then keep on reading from this file to get your next random number to assign to each racer's speed. That's it. And obviously, if let's say you have nothing left in the priority queue, so let's say what will happen is at some point, as you output the racers, so as each racer finishes the race, you'll output the racer to the screen, and you will not push it into the vector, which means it will not get pushed into the priority queue. Eventually, you will keep losing racers in your priority queue little by little, and eventually the priority queue will be empty, and there'll be no more racers left in the race, and then the simulation is not over. So that was this write-up portion here. Hopefully what I explained does make sense. I don't want to really give out too much step-by-step code because then I might be sort of giving out too much help. But really, not a very hard program, not too complicated. Just, just try to see how the priority queue maintains this. But of course, remember, when you first output element to the screen, that'll be the first place person. Next time around, when you pop an element off, and now the next, okay, sorry, let me just rephrase that. So when the first time a racer is popped off and distance is 0 or less, that would be the first rank, the first place sort of racer. And the next time when you pop an element off of this priority queue and that element is less than 0, that would have to be a second place racer and so forth. So I think I definitely over-explained this again, so I apologize for that, but hopefully this does make sense. So that's about it. Now let's go down to the specifications. So yeah, once again, do not use any of the fields of the racer type within PriorityQ. Use that less than or greater than operator to be able to verify which racer should be ahead in the queue. So don't use the dot speed, or no, sorry, dot distance traveled field. Use a less than operator or greater than to really be able to tell which racer is further ahead. And of course, here's my sample output. So I'll I'll have more outputs in code grade, but here's just our first one. So I just have my racers file, simulation file, and it outputs the rank of all these racers. So unfortunately, Wario wins, but I guess Wario does kind of play dirty, so it's not too shocking. But I guess Bowser being in last place makes sense. Bowser's pretty heavy, so he wouldn't be able to travel too fast. Although Wario is not so light either, but I guess Wario has his tricks to being able to win. So, and also for this program, I would recommend sort of having a separate PriorityQ.h file and have a separate main.cap file. But there's no rule for that because on code grade, it's going to just compile whatever you give it. So it'll just do a g++ star.cpp. So that way you can have separate files, have the same file will still work, but I would still recommend having a different header file for your PriorityQ class. But anyway, that's really about it. So hopefully this video did help you. So I guess happy coding and stay safe. And of course, till next time, take care.